Hey, my name is Doug Klein from the University of Kentucky. I'm coming to you today from my socially distanced classroom to be able to talk to you about projects. And so I'm going to share my screen with you, and we're going to look at a project that you're able to complete. So in this situation, what we have is we have a creek that we believe is being polluted, and we want to develop, wait, give me a second. I just got to clean my hands. I kind of feel like anytime there's anything dirty, I got to clean my hands nowadays. This is brought to you by Purell, whatever. But we know this creek's being polluted, and we've got to develop a device that is going to allow us to test it at multiple locations, right? And so we want to be able to go in and check here for certain things. So typically, when I think about that, I think about pH would be a great thing. So we can take and we can check the acidity of the water and be like very knowledgeable about what's going on, right? But we've got to do this in a socially distanced way, right? And I don't think that you have pH strips in your house, and maybe you do, and you're much cooler than I thought you were. But my other ways that I think about checking a creek is, I can get different sensors that look for different chemicals. Probably don't have that. But then you have the big thing of temperature. I know if I sit there and I have someone pour in a bunch of one chemical into a creek, that volume is going to change the temperature drastically in a very quick way. And so I can check for temperature very easily to determine if my creek's being polluted. The other way we're going to do that is we're going to be able to check for the cloudiness of the water or the turbidity of it, right? And so we can use those two things to make that happen. I'm going to talk about temperature first with you. And so in temperature, what we're going to do is we've got to develop a sensor, which we're going to use for our Arduino, to be able to predict the temperature that's there. So we're going to take a bunch of known values that we have, right? So in other words, I'm going to take a cup of water, I'm going to put my thermometer in it, and I want to see if it ends up at like 50 degrees, and then take the reading that the Arduino gives me when I put the thermistor in. Please bag that if you get open leads. And I can do the same thing at like 50 degrees, 55, 60, 65, all the way along the route and get multiple readings along that way, which is great. But one thing we might have to think about is if you don't have a thermometer at your house right now that's going to read effectively on that, right? Maybe it only reads like 98 degrees or something around there. So what we could potentially do though is we could take things that we know what their temperature is going to be about. So we know ice water is going to be right around 32 degrees. We could do some type of like research and determine what the temperature is of an average refrigerator and put a probe in that and see what temperature we get. We could like fill up a cup of water and let it normalize throughout the day to the house temperature and then say, hey, this is probably really close to what the temperature we keep the house. We do the same thing with a temperature outside and just get as many different samplings as we can in a scale that's mildly accurate. Right? But the goal is to have as many different points that we have of like known values or very closely known values to be able to work with and the voltage reading that relates to it, right? And so we're going to use that. We're going to develop our voltage divider here where we have our resistors in series, and then we're just taking a reading over the voltage drop of the second one, which in this situation is our thermistor, and it's giving us this chart. And we want to have a lot of those reading spots because we just have like really, really cold and really, really hot. Like it's really hard to predict what's going on in the middle, right? The more like points that we have to like sort of calibrate this sensor, the better off it's going to be. And so like the example here is if I just have my cold and my hot, I don't know truly that it's a linear fit. Like if it goes just linear from my low to my high right there, that can be scary. Because if it is a quadratic fit, right, or if there's a curve to it like that green line is, right, it could be very different in the middle as far as the temperature I get, like if it's right in the middle here or if it's right in the middle there, right? And so that's a big difference for how it works. And so we're going to use MATLAB to actually predict what those values are for us. The way we're going to do that is we're going to bring in the curve fitting toolbox, and it might already be installed in your MATLAB, but if not, it's just an add-in. So it's curve fit. And if you sit there, what it's going to do is it's going to take one value that you have, this is an array of values, and a second set of values, another array, just like we had up in this chart. So we have one set of values here, another set of values here. And then it's going to go and give us our best fit line, right? It's then going to sit there and predict out what the best fit line is, and gives us our standard formula right here. And we just know that P1 is 34.42 and P2 is 154.7. And so we know if we get a new reading, right, plug into this equation, we can get out the value or the actual temperature that it has. So we're going to do that for our linear fit, and then for our nonlinear or quadratic fit, we're going to do the exact same thing. So we're going to detail it as poly 2, and it's going to give us an additional value for it. Let me show you what that looks like within MATLAB. So in MATLAB, I've got the equation right here, right? My fit tool, my fit data is over here in my same folder here, right? There it is, right there. And all we're doing is, it looks just like the Excel table we saw a moment ago. And it's taking the data, all of it from column 1, and then all of it from column 2. And we are then plotting those against each other. So we're just doing a scatter plot. Let me show you what that looks like. I'm going to hold on right there, and we'll run and just have that breakpoint stop us. We're thinking about it. And so what it should be doing in a second, there we go. There it is. So what it's doing is it's taking those values and it's plotting them. So we've got our voltages along the bottom, and we've got temperatures along the top here. We can probably tell very easily I'm not checking water, right? Because 280 degrees is pretty hot for water. But we can see that I can very easily be using a digital sensor here, right? Because I've got values between 1 and 3.5. We know that any type of digital sensor is going to give us values between 0 and 5, right? And so those sort of fit with that paradigm of thinking. And so what I then have is, so I've got these two vectors right here, one being volts and one's being temps, right? And I can go down and I can do that exact same thing that we saw on PowerPoint, which I can just do a best fit for it, one being a linear relationship. And then what I'm going to do is I'm building an array here of between 1 and 4 by intervals of 0.1. So 1.1, 1.2, 1.3, all the way up to 4. We're running those values of that array or vector through this best fit equation and having it come out and plotting against those values. And so it's going to give us that plot of those values between 1 and 4. I'm then going to do the exact same thing with the quad fit, so exact same steps. It's just now we're looking for the best curve fit. And then we're just like setting up our legends. So let's see what that looks like. And so again, we sat there and we ran through the equation, all the values between 1 to 4 on every 0.1 as far as our value. And so now what I've got is I can sit there and be like, ooh, do I feel like this quadratic fit is better? Do I feel like this linear fit is better? And probably what I'd really want to do is I'd want to find something that's going to give me a value right around like 245. That's going to put it right there. And so I can get that a little bit more well-defined, or even up above like 350, but that might be out of my safety level. But then I can sort of help me define if it's going to be more of a linear fit or quadratic fit, right? But once I know that, right, and I know the equation that relates what my reading value is to my actual real value, right? All I have to do is do another analog read, get the value, have it go through that equation, and it can tell me what the temperature is, which is really kind of cool. And so we have that. And so we could also do the exact same thing for turbidity here. And so what turbidity is, it's really just cloudiness, right? And so I can sit there and I can very easily put like what clear water is, right? And I can try to develop something that's like a test situation over here. So my thought really is like creamer, right, or milk. And what we're doing is we're taking regular water, we're putting in 1 scoop of creamer, 2 scoops of creamer, 3 scoops of creamer, and 4 scoops, or whatever your like dirty agent is to do that. Because we don't have the actual, like, we can't reference this to known values of turbidity, but we can reference it to like scoops of that and then try to normalize it and then have it predict how many scoops are in it later on. So what's going to happen is we're going to sit there and take it and set an LED on one side of the bottle, shoot light through it onto a photoresistor. And the hope is that the one with no scoops in, more light's going to get through, and the one with a lot more scoops, not nearly as much is going to get through because it's going to have all this refraction along the way. We can then sit there, build that into our exact same thing where we have the first column, which is our number of scoops. Second column is our voltage readings, right? Or actually it's vice versa, but then we can sit there and throw that into our best fit plot and be able to determine if it's linear or quadratic and be able to develop a tool that's going to tell us if it's how many scoops are in there. So then I build up my structure, I put a new bottle in, and it tells me how many scoops of creamer or whatever is in that cup, which is kind of cool. So we can then sit there and finish up the project and sort of finish out the device. So we've got it to where this kid has built the turbidity testers. They've got an LED here and they've got a photoresistor there. They've got to be kind of like similar in height. You've got to be able to have a bottle with smooth sides on it. I don't recommend using blue anything. I like the color blue. I work for UK. But I would try to make it to where it's just getting cloudier because like tinting it doesn't really change the turbidity. But so we have that. We can get a value for our temperature and we can get a value for our turbidity. And now we can sit there and develop a physical device that's going to read out the values for us. So we can have a servo right here where we're reading out the values between 30 and 120 in our temperature, right? And we would have just like, this would be telling us, hey, if it's 30, it's really a 0 on my servo. And so my servo will go right there. It's 120, it's a 1. If it's like the exact middle of that, it's 0.5. And we sort of have the servo predict that way. And we can do the exact same thing with this, with the turbidity, whether it be like 1 scoop, 2 scoop, 3 scoop, 4 scoop, right? And we have be that the highest number of scoops is 1, the lowest number of scoops is 0, and then just the percentage of that allows it to sort of project. And so we can build this device and be able to have it as sort of like a mobile station where people are able to go. I can model up the parts and hit that point in my project. I've got plenty of data to work with. I've got some modeling within that. I'll need to build a flow chart, right, to determine with the code what's going on there so I can communicate well. But I've got good bones of a project right there. And so that's something that we can proceed with and you can work on.